Good afternoon. My name is Chad Ross, and I'm the Manager of Industry Relations and Total Store Collaboration here at the Food Marketing Institute, or FMI. FMI and I am pleased to welcome you to today's webinar sponsored by IFCO. A couple of housekeeping notes. Be sure to enable your computer's audio or speakers with the volume turned up. Also, at the end of this presentation, our presenters will be answering questions you submitted through the chat function. Today's program is the second in our three-part series sponsored by IFCO entitled Remove the Risk, using data to drive fresh produce growth. Today we'll learn just the facts, how reusable assets can help retailers and growers achieve their zero waste goals, an enlightening topic in today's business environment. Our speakers today are Hilary Femal, the Vice President of Global Marketing for IFCO, and Beverly Sauer, the Senior Chemical Engineer, Senior Life Cycle Assessment Analyst for Franklin Associates. Guys, the floor is yours.
Today's webinar focuses on how retailers and growers can utilize reusable assets to achieve their zero waste goals. We'll start by exploring the relationship between zero waste initiatives, reuse, and recycling. Next, we'll take a look at a recently published life cycle assessment of reusable plastic containers, or RPCs, and single-use cardboard boxes in fresh produce applications. And finally, we'll hear about the impacts of those two life cycles on waste, natural resource consumption, and environmental pollution. Let's look at the relationship between zero waste, reuse, and recycling. Zero waste is a philosophy that encourages the redesign of resource life cycles so that all products are reused. The EPA says that achieving net zero waste means reducing, reusing, and recovering waste streams to convert them to valuable resources with zero solid waste sent to landfills. And the EPA also instructs us how to achieve this in its waste management hierarchy. At the top of the inverted pyramid are source reduction and reuse, the two most preferred methods of waste reduction, followed by recycling or composting, energy recovery, and finally, treatment and disposal, the least preferred method. So let's just focus on reuse and recycling. Why is reuse preferred to recycling in the EPA's waste management hierarchy? It comes down to recycling needing remanufacture. The impact of this key difference between reuse and recycling will become very evident when we review the results of the life cycle assessment. But before we begin, I'd like to show a short video to familiarize you with IFCO as a company and also the reusable plastic container life cycle.
At IFCO, improving efficiency for our customers' supply chain is the goal. From transportation to labor to materials, we know our customers' businesses inside and out, and we make sure you will always have what you need when and where you need it. As a company committed to environmental sustainability, our solutions reduce natural resources and energy consumption while also reducing waste and greenhouse gas emissions. IFCO RPCs make for the ideal produce packaging solutions, reducing supply chain costs while delivering superior quality produce. Using efficient logistics, IFCO helps to minimize the need to carry an inventory of RPCs. Reducing cost and seamlessly integrating into existing packaging operations, our RPC cycle begins when IFCO delivers clean RPCs to leading growers and shippers when and where they're needed. Once packed with produce, the RPCs are loaded onto outbound trailers destined for grocery distribution centers. IFCO's RPCs maximize the use of trailer space through efficient stacking, which also better protects produce while in transit. The rigid construction supports weight to eliminate crushing, and ventilation reduces heat retention. At the distribution center, the innovative design of the RPCs make for easy product identification. The ergonomic handles reduce injuries, while their sturdy construction creates strong mixed pallets that hold up perfectly in the wet room environment. Over 85% of produce managers surveyed noted that they preferred RPCs to corrugated boxes. Once arrived at the grocery store, RPCs can be used for both display and restocking and can easily be returned to IFCO after use. The process is simple and seamless. Back at IFCO's AIB certified service centers, RPCs are then inspected, cleaned, dried, and shipped back to growers to begin the cycle again. IFCO customer service is available night and day to deliver the very best assistance to our valued customers. IFCO provides cost-effective, efficient, and environmentally responsible reusable transport packaging solutions to the world's most successful retailer manufacturers and growers. IFCO Systems is your global partner in reusable packaging solutions.
As you just saw in the video, IFCO's reusable plastic containers are reused again and again. We know reuse is better for the environment than recycling, but just how much waste does it reduce? And what are the impacts on other factors such as water or energy consumption, CO2 emissions, or pollution? In order to find out, it's necessary to conduct a thorough life cycle assessment with qualified practitioners. So in February of this year, IFCO finalized our third LCA with Franklin Associates. The purpose of this assessment was threefold. First, we wanted to determine the environmental burdens associated with our RPCs in North American operations. Secondly, we wanted to obtain data that would aid us in our own internal decision-making. And finally, we wanted to generate results that we could use with our customers and other supply chain partners regarding the environmental impact of using our products. So now to take us into the life cycle assessment and results, this is Beverly Sauer of Franklin Associates.
As Hillary mentioned, we've done several updates of the produce container LCA over the past several years, updating the study when newer data has become available on RPCs and corrugated. Today I'm going to walk you through the latest update, which was just completed in March of this year. First, I'll start with a brief overview of our LCA credentials. Franklin Associates is the original life cycle consulting firm in the U.S. Our founders pioneered the life cycle methodology in the early 1970s, and we've been doing life cycle studies ever since. Our life cycle services include data development, life cycle reports, and customized interactive models that allow users to evaluate a whole range of scenarios. Our work helps our clients understand the life cycle impacts of their activities so they can target efforts to improve their environmental performance. Our studies follow the international standards for LCA, ISO standards 1440 and 1444. This slide shows just a few examples of our clients, which include federal, regional, and local agencies and organizations, as well as private companies and industry associations. Before I get into the specifics of the produce container analysis, let me give you a brief overview of life cycle assessment, or LCA for short. ISO 1440 defines LCA as the compilation and evaluation of the inputs, outputs, and potential environmental impacts of a product system throughout its life cycle. This flow diagram illustrates the general sequence of steps evaluated for a product's life cycle, starting with raw material extraction, continuing through manufacturing of the product, distribution and use, and management of the product when it's reached the end of its useful life, hopefully cycling back into raw materials for another use. For some products, like RPCs, the life cycle includes reuse, which delays disposal or recycling, and as shown in the figure, bypasses raw material extraction and manufacturing to extend the useful life of the product. LCA identifies those life cycle stages and even individual materials and processes within the life cycle stages that are the main contributors to environmental impacts. This is valuable information to help you effectively focus efforts to reduce your system's environmental footprint. One of the most important benefits of LCA is that it gives you a scientific, quantified basis for making decisions. Why is this important? Well, when weighing options, product designers, manufacturers, and consumers are faced with many choices that often have different characteristics or potential trade-offs. And you often can't make an informed decision based solely on these qualitative differences. Produce boxes are a really good example. RPCs are made from fossil fuel resources. They're heavier than corrugated boxes. They require return, transport, and cleaning after each use, but they're reused many, many times. Corrugated boxes, on the other hand, are made from renewable resources. They have recycled content. They're recycled at high rates, but a box must be manufactured for every shipment that's made in a single-use box. Based on these different characteristics of the two systems, you can't really tell which one has lower environmental impacts. This is where LCA comes in. LCA is a science-based method for translating qualitative differences like this into quantified impacts for each life cycle stage so that you have a comprehensive environmental footprint for each system that allows you to make informed decisions about the different systems. So, what do the life cycles of RPCs and corrugated boxes look like? Let's take the general diagram I showed you earlier and review the differences for the two produce packaging systems stage by stage. The first stage is raw material extraction. For RPCs, the stage includes extraction of the petroleum and natural gas resources that are used as feedstocks to make the plastic resin used in the RPCs. For the corrugated boxes, which are made from a mix of virgin and recycled fiber, the raw material extraction includes harvesting trees for the virgin fiber content of the boxes and collection of post-consumer corrugated boxes used for the recycled fiber content. The next stage is manufacturing. For RPCs, the manufacturing stage includes converting the petrochemical feedstocks into resin, transporting the resin to the manufacturing location, and injection molding of the RPC containers. For corrugated boxes, manufacturing includes transporting timber or OCC, old corrugated containers, to mills, the pulping and paper making and box converting steps that are used to convert these raw materials into finished produce boxes. And for both systems, the finished containers are then unitized for shipment to users. And this life cycle stage also includes the production and disposal of ancillary packaging, such as pallets, stretch wrap, or strapping that might be used in shipping the containers to the users. The distribution and use phases for both container systems include transporting the new containers to users, in this case growers, and transporting containers filled with produce from growers to retail distribution centers and then on to stores. For RPCs, this stage also includes backhauling the empty RPCs from retail stores to retail distribution centers and then on to IFCO service centers where the containers are cleaned and sanitized and then reissued to the next user. The use phase for corrugated boxes ends with the supply of empty boxes that are ready for recycling. The last stage is management of containers at the end of their useful life. RPCs that can no longer be reused are transported to recycling facilities where they're reground and molded into new RPCs. Corrugated boxes are transported to mills where they're repulped and used to make new boxes or other recycled paper products. For both systems, containers that are not recycled are disposed, with approximately 80% going to landfill and about 20% disposed by waste-to-energy combustion, and this is based on U.S. National Waste Disposal statistics. In the produce container analysis, we looked at the 10 different produce types listed here on the slide. These 10 commodities were selected because they're high-volume commodities, and together their combined annual sales accounts for almost half of total retail produce sales. The 10 commodities also represent a variety of produce sizes, shapes, weights, growing locations, and box sizes used for shipping, so they provide a good representation of the overall retail produce landscape. Transportation throughout the supply chain was based on a mix of primary collected data and national statistics. For shipment of produce from growers to retailers, we used weighted average commodity shipments by truck and rail compiled from USDA data. We also used USDA statistics to identify the grower locations that ship the greatest volumes of each of these commodities over a 3-year average. For example, apples are mainly grown in Washington, New York, and Michigan, while oranges are grown in Florida, California, and Texas. So to model the distribution distances, these grower locations were mapped against the cities that had the greatest concentrations of distribution centers for the top 75 food retailers in the U.S. and Canada in 2010. For return shipping of RPCs, the DC locations, distribution center locations, were then mapped against 6 IFCO service center locations where the RPCs are cleaned and reissued to the next user. I should note that 2 new service centers that were recently opened in Canada were not included in the study because we like to have a full year of operating data before including a facility in the models. However, the effect of adding these new centers would be to further reduce the net average return transport reissue distance for the pooled RPC network. As I mentioned earlier, we looked at a variety of RPC sizes and weights based on those that are most commonly used to ship these 10 commodities. For corrugated, we looked at 2 box types for each type of produce. We looked at display-ready containers, or DRCs, where the boxes are used to ship the produce from the grower to the store and then also used to display the produce at the retail store. And we looked at non-display ready containers, or NDCs, which are used to ship produce from growers to retail, but the produce is moved into a different container for store display. In the study, we only evaluated recyclable corrugated produce containers. We did not include non-recyclable waxed corrugated boxes, which are becoming less widely used. For modeling the produce container systems, we used reliable, publicly available data wherever possible in order to maximize the transparency and credibility of the study and results. Data for production and combustion of fuels used for process and transportation energy throughout the produce container life cycles were largely based on government reports and statistics. Data for production of plastic resin used in the RPCs is from a 2011 study for the Plastics Division of the American Chemistry Council, and data for plastic recycling is from a 2010 recycled resin study that was sponsored by several plastics industry associations. All of these data are available in published reports as well as in the publicly available US LCI database. For corrugated, the container production modeling is based on information in a 2014 LCA that was conducted by the Paperboard Industry's National Council for Air and Stream Improvement, and the corrugated container recycled content is from an August 2016 press release by the Corrugated Packaging Alliance. Primary data that was collected specifically for this study included data from IFCO on RPC weights and composition and transportation distances for distribution of IFCO produce RPCs in North America. RPC cleaning processes were modeled using data from IFCO service centers, and IFCO suppliers provided data for manufacturing of RPCs. IFCO also provided data on lifetime trip rates for RPCs and losses of containers during their pooling operation cycling. In addition to transportation distances, IFCO also provided data on packing configurations for the various transportation steps throughout the RPC life cycle. For corrugated boxes, the packing configurations were based on data from a variety of sources, including growers, distributors, repackers, and fiber box suppliers. Where specific data were not available, packing configurations for fiber boxes were estimated based on maximum truck loading. Let's take a minute to talk about the balance between recycled content and recycling rate of corrugated containers and how it affects results. Corrugated boxes at retail locations have a very high recycling rate, and some of the recovered boxes are cycled back into corrugated production to provide recycled content for new corrugated boxes. Excess recovery of boxes, above what's needed to sustain the recycled content of the produce boxes, gets used to make other products so that the corrugated produce box system gets a credit for that fiber displacing a mix of virgin and recycled fiber going into other uses. Because the fibers in paperboard get shorter with repeated recycling, corrugated with recycled content is not a fully equivalent substitute for virgin fiber, so that's why we modeled a mix of virgin and recycled fiber displacement. When we go through the results slides, the reduction in impacts associated with the use of recycled content in the boxes, those benefits are included in the results you'll see for the box production stage, while the impacts associated with end-of-life recycling and credits are included in the end-of-life stage. And when we go through the results slides, you'll see that the corrugated recycling and displacement modeling results in a net end-of-life savings for some results, but other results have a net end-of-life burden. As I mentioned previously, the produce applications that were analyzed in this study were selected based on those that had significant system volumes and that provided a good representation of the variety and mix of fresh produce in North America. Each of these commodities was evaluated individually, and a composite average was also modeled based on the relative shipments of these 10 commodities in 2013, and that mix is shown in the table here. The results varied to some extent for the comparisons of RPCs and corrugated across the different individual produce types, and this was due in part to differences in produce weights and packing densities. For example, carrots are heavy and packed quite densely and compactly in the containers, while bell peppers and other types of produce may be lighter or rounder in shape, so they don't pack quite as compactly. The results were also influenced by differences in the weight and capacity of containers that are used to ship the different produce types, as well as distances from the growers to distribution centers, which are longer distances for some commodities compared to others. However, the general trends and results for comparisons of RPCs versus corrugated were quite consistent. The results I'll be showing in just a few slides are based on shipping 1,000 metric tons of the composite produce mix using RPCs and using corrugated boxes. In the study, we evaluated 8 commonly used LCA metrics. Energy, solid waste, and water consumption are basic measures of resource consumption and waste disposed. Other results are calculated based on the mix of emissions released to air and water over the life cycle of each system. Many of you are likely familiar with at least some of these, like global warming potential, but I'll briefly run through a description of the others. Acidification looks at the potential for emissions to contribute to acid rain, which can damage forests and plant life and erode building exteriors. Eutrophication evaluates the potential for emissions to serve as excess nutrients in surface water, which causes rapid growth of aquatic plants and reduces the amount of oxygen in the water available for other aquatic species, so this can result in impacts like fish kills. Ground level smog creates haze and can also contribute to health problems like asthma, and ozone depletion, or the destruction of the Earth's protective ozone layer, allows more ultraviolet radiation to reach Earth's surface, and this can increase risks of cancer and other health issues or affect plant and animal life. You'll see that some of the results here are expressed in terms of equivalence, abbreviated EQ. For each impact category that's reported in equivalence, the various emissions that contribute to that impact are all normalized to a common reporting basis. For example, the global warming effect of a kilogram of methane is 25 times the impact of a kilogram of CO2. So methane emissions are multiplied by 25 to convert them to the reporting basis of CO2 equivalents. And the same approach is used for all these other impacts that are expressed in equivalence of a reference system. Now that we've covered the background, we can start looking at the results. But first we have to go over some general description of how to read the charts that I'll be showing on the next several slides. So you can see that a pair of bars is shown for each system. The first bar is color-coded by life cycle stage so that you can see which stages make the largest contributions to the results. For RPCs, you need to keep in mind that the container cleaning impacts are grouped in with the container production results. Where you see negative results below the zero line, that represents net credits, where the benefits of end-of-life recycling for a system are greater than the impacts for the recycling processes and disposal of containers that aren't recycled. The second dark-colored bar in each pair is the net results, which is the total impacts minus the credits. So then we draw a horizontal line at the level of the net RPC results, and the percent savings for RPCs compared to corrugated is calculated based on the difference between net RPC results and net corrugated results. As I noted earlier, we looked at both DRCs and NDCs, but the results were very similar, so the slides just show results for the display-ready corrugated containers. So now we can talk about energy results. So the total energy demand for each system includes the energy used for process and transportation energy throughout the life cycle, as well as the energy content of the raw material feedstocks for each container. That would be the oil and gas feedstocks for RPC resin and the wood fiber energy content for corrugated. So in looking at the left-hand bar for RPCs, you can see that the total energy demand is fairly evenly split between the container production and distribution transport stages. And actually, for the container production stage, the largest share of that by far is for the cleaning processes. So the energy for distribution and transport is mainly for the extraction and combustion of the diesel fuels used in the transportation steps, and also the energy associated with the cleaning. And that includes energy for production of cleaning chemicals, energy used in the cleaning process, and energy for producing the packaging that's used to transport the cleaned RPCs. For corrugated, the largest share of energy is for manufacturing the boxes, and that's because, as we noted earlier, you have to make a box every time you make a shipment in a box, since each box is only used once before it's recycled or disposed. The corrugated systems show some significant energy credits for the fiber production that's avoided by use of the fiber from excess recovered boxes. And that's because it takes less energy to recycle boxes than it does to make new virgin paper fiber from wood. Taking all that into account, we see that the overall net energy savings for using RPCs compared to DRCs is 64% savings. Next, we'll look at global warming potential results. For RPCs, you can see that again, the largest share of results are associated with distribution transport, and that's associated with the production and combustion of fossil fuels used during transport. And the next largest contributor is the container production stage. And the largest contributor within the container production stage is the cleaning processes again, and that includes the global warming potential impacts associated with the production of the cleaning chemicals and the use of energy for the container cleaning processes. For corrugated boxes, the majority of global warming potential is again associated with production of the containers. You'll note that unlike the energy results, there's no net global warming potential credit for excess recovered boxes, and that's because even though paperboard recycling uses less energy than virgin paperboard production, recycling mills rely mainly on fossil fuel energy, and so they have higher greenhouse gas emissions than virgin paperboard mills, which use a lot of wood-derived energy. So overall, for the composite produce mix, RPCs showed 31% lower life cycle global warming potential impacts. For ozone depletion, you can see that the results for RPCs are really dominated, in this case, by the emissions from the production and combustion of fuels used for distribution transport, while for the corrugated boxes, the bulk of the impacts occur during production of the container. There are some pretty substantial net credits for the virgin paperboard production emissions that are avoided by the recycling of excess recovered corrugated boxes, but overall the net savings in ozone depletion impacts for RPCs compared to corrugated is 78%. For water consumption, container cleaning, which is included in the container production phase, and distribution transport are both significant contributors to the results for RPCs. For the transport, the water consumption is associated with the extraction and processing of the diesel fuel, while for the RPC cleaning phase, water is consumed in the cleaning process itself, as well as in the production of cleaning chemicals and packaging materials, and in production of the electricity used in the cleaning process. For corrugated containers, the container production phase is again the largest contributor to results, and water consumption in this phase is due both to direct process consumption of water in the pulping process, as well as evaporative losses of water that are associated with generation of electricity used in manufacturing processes. End-of-life recycling and disposal of the fiber containers show credits for water consumption due to the displacement of virgin fiber production by the fiber from the excess recovered corrugated boxes. Overall, the net water savings for RPCs compared to DRCs is 80%. Emissions that contribute to acid rain are generally associated with the combustion of fossil fuels. For RPCs, distribution transportation and the cleaning results that are included in the container production stage together contribute the bulk of the acidification impacts. This is due to the combustion of fossil fuels in the transport vehicles and also the emissions associated with the cleaning process energy, as well as the production of cleaning chemicals. For corrugated systems, the container production process is again the largest contributor to acidification impacts, and those emissions are associated with generation of electricity and combustion of fossil fuels that are used in the manufacturing operations. Overall, the net savings in acidification for RPCs compared to DRCs is 66%. Emissions that contribute to eutrophication are generally associated with combustion of fossil fuels and waterborne emissions from paper mills. For RPCs, nitrogen oxide emissions from diesel fuel combustion make distribution transport the largest contributor to eutrophication results, and that's followed distantly by the container cleaning step, which includes the emissions from the production and use of cleaning chemicals. For corrugated, container production again dominates the results, and this is due to the emissions from production and use of pulping chemicals, as well as emissions from combustion of fuels at the containerboard mills. However, there are some eutrophication credits for virgin fiber production that's displaced by the box recycling, but overall, the net potential reduction in eutrophication for RPCs compared to DRCs is 86%. Similar to acidification, the emissions that contribute to smog formation are generally those associated with combustion of fossil fuels. So smog results for RPCs are again dominated by impacts from distribution transport for the combustion of fuels in the transport vehicles, and to a lesser extent, emissions associated with cleaning processes. For corrugated, releases of nitrogen oxides and VOCs, volatile organic compounds, from the processes at pulp and paper mills contribute the majority of the photochemical smog impacts. There are also pretty substantial smog contributions from distribution transport. Overall, the net decrease in smog impacts for RPCs compared to DRCs is 42%. The last results category we looked at was solid waste. For RPC systems, you can see that several life cycle stages share in the contributions to the generation of solid waste. The largest sources of solid waste are end-of-life disposal of the small percentage of RPCs that are lost during use, for example, due to theft, and are assumed to eventually end up disposed as solid waste. There are also solid waste associated with the cleaning process, which includes waste associated with production and use of process energy, as well as waste from production of cleaning chemicals and packaging materials. And there are also fuel-related wastes from container distribution transport. For corrugated, the bulk of solid waste generation is process and fuel-related wastes generated during container production, followed by wastes associated with the 5% of containers that are not recycled after use. The net reduction in solid waste generation for RPCs compared to DRCs is 86%. Overall, RPCs showed substantial savings compared to corrugated in all categories evaluated in the LCA. The individual results figures showed that RPCs had higher impacts for distribution compared to corrugated due to the return transport of RPCs for reuse, but corrugated boxes had much greater impacts for container production. Overall, the benefits associated with repeated reuse of RPC containers that circulate in a controlled, optimized pooling system are greater than the added impacts for backhauling and cleaning between uses. Although corrugated produce boxes are made from renewable resources, have recycled content, and are recycled at very high rates, these positive characteristics are outweighed by the burdens incurred by manufacturing a box for each shipment made in a single-use corrugated box.
Thanks so much for taking us through that, Bev. When you look at the entire life cycle of a reusable system, it becomes clear that reuse not only dramatically reduces solid waste, but other important impacts as well. So for retailers and growers committed to achieving zero waste, RPCs are an effective way to help meet these goals. Just look at this quote from Kroger's sustainability report last year. It says, "Kroger is committed to being a positive force for change when it comes to sustainable business practices, and CHEP and IFCO play an important role in our effort to meet our zero waste goals and continuously improve the sustainability of our supply chain." For IFCO, it's not enough that our products and services help reduce the environmental impact of our customers' businesses. It's important that we ourselves operate sustainably as well. We and our parent company, Brambles, make good on this commitment by first setting ambitious goals. Amongst other goals, we've set a target to achieve zero product waste to landfills and a 20% reduction in CO2 emissions by 2020. Our 2020 sustainability goals emphasize our commitment to making the world's supply chains more efficient, investing in our people and communities while conserving and enhancing the natural resources that our businesses depend on. And by linking our goals to the United Nations Sustainable Development Goals, we've aligned our sustainability strategy to global priorities. And this gives us a common platform for collaboration with our key stakeholders on critical sustainability issues, such as deforestation, climate change, future resource constraints, and the resilience of food supply chains. It's been really encouraging to see that these efforts have not gone unnoticed. We've been included in the Dow Jones Sustainability World Index for the third consecutive year, with Brambles achieving second place in our industry category. I'd like to focus on two initiatives specific to RPCs. As you just heard from Bev, the majority of the environmental impact of RPCs is driven by transportation, so we're continuously seeking ways to be more efficient in this area. This is achieved through network optimization, a process through which we continuously evaluate the flows of RPCs around North America and strategically locate our service centers to minimize transport distances. And as RPC volumes continue to grow each year and we open more and more service centers, these transport distances shrink even further. We also want to minimize the impact of our operations within those service centers. So to this end, IFCO has developed Smart Guardian, our proprietary wash process control system. Smart Guardian combines sensors installed throughout our wash equipment with sophisticated software which monitors water and energy use and also water pressure, temperature, and detergent use on all of our washing machines. In this way, we are continuously monitoring our consumption and finding best practices for reducing that consumption at each of our 80 service centers around the world. Now we'd like to open it up for Q&A, and we did have several questions come through the chat, so thank you all for those. So Bev, if you are ready, I will just read these to you. The first one, did the LCA look at petroleum extraction? How can a non-renewable resource have a lower impact than a renewable one?
The first question's easy. Yes, the LCA goes all the way back to raw materials, and that includes impacts for extraction of oil and gas for plastics and forestry operations for paperboard. Now, regarding the renewable versus non-renewable question, there's a couple of things that come into play here. First of all, renewable doesn't automatically mean a product has lower impacts in all regards compared to a product that's made from non-renewable materials. As I mentioned earlier, a lot of times you have trade-offs. So, for example, producing a pound of a bio-based material might have lower greenhouse gas emissions than a pound of material that's made from petrochemicals, but the bio-based materials often have higher eutrophication and water consumption impacts. So, for example, that could be due to agricultural processes if you're looking at a crop that uses fertilizers and is irrigated. Or in the case of paperboard, we saw on the results slides that there was a lot of water used in eutrophication emissions for the processes at pulp and paper mills. Also, even if the renewable product does have lower impacts on a pound-for-pound basis, an LCA compares products based on fulfilling the same function. In this case, we were looking at the function of making a number of shipments required to deliver 1,000 tons of produce. So since RPCs are reused over and over again, the impacts from making each RPC are divided over all the uses of that RPC, so the container manufacturing impacts that are allocated to each trip become very small. But since the corrugated boxes make only one trip, you have to make many, many more pounds of corrugated boxes to make that same number of produce shipments, and so you end up with higher net impacts for the fiber box systems.
Great, thanks so much, Bev. The next question, why weren't wax or wax alternative boxes included in the assessment?
Well, we wanted the comparison to be fair and unbiased, so we used conservative assumptions for corrugated. The reason for using wax coatings on produce boxes is to keep the boxes from getting soggy and weak if they get wet. But then the wax coating prevents them from being recyclable. And as I mentioned earlier, wax-coated boxes aren't as widely used anymore since now there are newer additives that can be used to give boxes wet strength but still allow the boxes to be recycled. And since modeling unrecyclable wax boxes would have been unfavorable for corrugated and wouldn't reflect current trends, we only looked at recyclable corrugated. I should note, though, that we couldn't find data on the specific composition of the repulpable additives that are used for corrugated wet strength, so we weren't able to include production of those chemicals in our modeling. So the results I presented earlier did not include the additional impacts that would be associated with using those chemicals in the boxes.
Great, thank you. Next question, what does it mean that the study was peer-reviewed?
The ISO standards for LCA require that when you are going to use a study to make public comparative statements about competing products, that study has to be reviewed by a panel of external independent experts. and that's known as a peer review or critical review. And the reason for having a peer review is to ensure that the study was conducted in a fair and unbiased way and used appropriate data sources and assumptions, that the study followed the ISO requirements for LCA, and that the results and conclusions of the study were accurately reported without any overstated claims or greenwashing. And the panel that reviewed our LCA included three well-respected LCA experts. We had Dr. Susan Selke, who is a professor of packaging at Michigan State University. We also had Dr. Marianne Curran, and she was an LCA manager at the U.S. EPA's Office of Research and Development for many years before she retired a few years ago and went into private consulting. And finally, we had Dr. Shelley Miller, who is with the University of Michigan Center for Sustainable Systems. And the way the peer review process works is we would send the report to the panel. They review it against the ISO standards, and then they let us know if they have any questions about the study or if they think any changes need to be made. Then we respond to all of their comments and make any necessary revisions to the study and send the report back to them. And they check that we have responded to their satisfaction to all their comments. And finally, they issue a final approval letter. And at that point, then the study is essentially cleared to share publicly.
Okay, thanks. And I think this will be the last question we have time for. I've seen studies by the corrugated box industry which claim corrugated boxes are more sustainable. How can two studies come to different results?
The Corrugated Packaging Alliance has published a couple of life cycle assessments in the past several years, and we actually used process data from those studies to help us model the produce boxes, the corrugated produce boxes. Now, the CPA studies show the progress that their industry has made in reducing the environmental impacts for corrugated boxes, from adding more recycled content to improvements in processes to reduce emissions and process energy. But their studies just look at average corrugated boxes. They don't compare corrugated boxes with alternatives in specific applications. I'm not aware of any comparative LCAs of corrugated and RPCs that have been done by the corrugated industry. Couple of other points. The corrugated industry LCAs are based on national average corrugated boxes, which currently have about 50% recycled content. Now, produce boxes have lower recycled content than industry average boxes, and that's because the produce boxes have to stand up to shipping heavy loads of produce, including produce that might still be wet or that's stored in damp conditions. So the produce boxes need a higher percentage of longer, stronger virgin fiber compared to the industry average boxes. Also, when you see a claim about sustainability, it's important to understand the basis that's being used for the claim. This kind of goes back to my slide with the balances. Is the sustainability claim being made just on qualitative issues, renewable resources, recycled content, recyclability, or is it based on a quantified LCA for a specific application? And there's just one more other thing that I wanted to point out. Our LCA showed that the pooled RPC system has advantages over corrugated boxes for produce applications. But our study is not meant to suggest that corrugated boxes are not a good product. Now, if you're looking just at one-way container options, corrugated is a very good option in a lot of packaging applications, and it keeps a lot of material out of landfills due to its recycled content and high recycling rate. So you shouldn't necessarily draw broad conclusions about other applications based on the results and conclusions of a specific LCA.
All right. Thank you so much, Bev. So that concludes today's webinar, and I'd just like to invite all of you to join us again on June 8th at 2 Eastern for our final webinar in the series called The Bottom Line, Fact-Based Decision-Making Drives Fresh Produce Supply Chain Savings. And this one will focus on some research that was performed by Cal Poly, Drs. Jay Singh and Kaushik Saha, around indirect packaging costs throughout the fresh produce supply chain. So we hope you'll all be able to join us for that on June 8th. And that concludes our webinar for today. So thank you all very much and have a good rest of your day.